Hello, everyone. So today we are starting Unit 9, and I personally feel like Unit 9 kind of has two sections that are semi-related, semi-not related. So today we're basically going to be talking about the first section of Unit 9, which is all about thermochemistry. So we talked about thermochemistry way back in I think it was Unit 6. It was the first unit of this new semester. And so today we are going to continue with thermodynamics, learn a few new things. We're going to start with it today, get through like 90% of it, and kind of wrap up tomorrow or next class with the other like little piece of that. I just thought doing it all in one day might be a little much, especially the last piece that we're learning. And then the second part of this unit is really electrochemistry, and they are related and not related at the same time, I guess is the best way to think through that. So we're going to start with entropy and Gibbs free energy today. So we're going to start by talking about a thermodynamically favored process. It used to just be called a spontaneous process, but College Board has kind of moved away from calling things spontaneous and saying instead thermodynamically favored. And what that means is that it occurs without outside intervention. So this reaction will happen all on its own. Now, that doesn't necessarily mean that this reaction is going to occur very quickly or that this reaction is not going to be slow. That's dependent on kinetics. So remember, thermodynamics and kinetics are two different things. Just because a reaction is going to happen, it's thermodynamically favorable does not mean kinetically it's even going to be perceptible. One example of that is like a diamond. Diamonds decay, but it takes so long for it to do that we don't see it happen. So that's just one example of thermodynamically favorable, but slow. All right. Kind of our two big new concepts that we're going to talk about are entropy, which is related by S, and free energy, which is G. So we're going to start by jumping into entropy and what entropy is. So entropy, or it's S, it's a measure of randomness or disorder. And it's all associated with probability. But just think through this. There are more ways for something to be disorganized than organized. And really, we're going to be looking at how is our entropy changing. So entropy increases going from a solid to a liquid to a gas. If you think about that, the particles in a solid are very structured. They're close together, they're tightly knit, and they just kind of vibrate in place. Whereas in a liquid, they are going to be moving a little bit more, so it's just more disordered. There's not organization there. And then in a gas, they're flying around any way that they can. So we see a change in entropy in phase changes. Entropy usually increases when solutions are formed. Remember, a lot of times in solutions, our substances are going to dissociate or break apart into their ions. So again, we just have more pieces, so more likelihood to be disordered. And then entropy increases in a reaction when more atoms or molecules are formed. So basically, when we have more moles being formed, we're going to have greater disorder. Again, there's just more stuff, so there's a greater chance for it to be disorganized. And then entropy increases with increasing temperature. Well, what happens when we increase temperature? When we increase temperature, our molecules start moving faster. And again, the faster our molecules move, the more chance there is for them to be disordered and disorganized. All right, so our second law of thermodynamics says, in any spontaneous process or thermodynamically favorable process, there's always an increase in entropy of the universe. The energy of the universe is a constant, but the entropy is increasing. All right. So what I want us to do now is look at these two reactions and predict whether or not our sign of delta S, or our change in entropy, is going to be positive or negative. All right. So for my first one, it says the thermal decomposition of solid calcium carbonate. So a couple of things that we should be looking for is really kind of like these things on our list. So is there a phase change? Are we making more or less molecules? Is there a solution? Like what's going on? And we can see in this one that number one, I see a couple of things. So on my left side, on my products, I have 1 mole. And on my right side, I have 2 moles. So I am making more atoms or molecules, 1 mole to 2 moles. All right, the other thing I see is that I'm starting with a solid, ending with a gas. So again, I have that phase change going on as well, going from solid, which is really ordered, to gas that's much more disordered. So my delta S here would be positive, just because, again, those two things. So we have more moles on the product side than we do on the reactant side. And as well, we have that phase change from a solid to a gas. All right. For our next one, all right, I want you guys to take a minute, look at it, and pause the video if you need to, and figure out what you think the change in entropy would be. Again, look at your list, see if you can figure it out. So go ahead and pause it if you need to. Okay. So for this one, all right, we are all in gas the whole time. So we have no phase change going on. There's no solutions being formed. But what we do see is we go from 2 moles to 3 moles. So we're making more moles again. So this one is also going to be a positive. Oh, I'm sorry. Man, guys, I read that reaction. I totally did not follow my signs. We're going from 3 moles to 2 moles. So we're going to have a negative entropy there because we're going from 3 moles down to 2 moles. So we have less moles, so we have less disorder. So we would have a negative delta S there. Okay, let's move on. So the third law of thermodynamics says that the entropy of a perfect crystal at 0 Kelvin is 0. But what we're going to look at is how can we calculate our delta S? Well, our delta S of our reaction is equal to the sum of our delta S of our products minus the delta S of our reactants. You guys may notice that looks like a very similar equation. It is very similar to our delta H equation that we learned quite a while back. So delta H of our enthalpy is equal to the sum of our delta H of our products minus the sum of the delta H of our reactant. So very similar things going on there. All right, so let's go ahead and solve our first one right here. So it says, given the standard molar entropies, calculate delta S for the reaction. All right, we have our reaction right here. So we have 2 moles of aluminum plus 3 moles of magnesium oxide yields 3 moles of magnesium plus 1 mole of aluminum oxide. All right, so the delta S of our reaction is going to be equal to the sum of the entropies of our products times the sum of the entropies, or minus the sum of the entropies of our reactants. So I have, let's start with my products. I have 3 moles of magnesium, and magnesium's entropy is 33.0 joules per Kelvin, plus 1 mole of aluminum oxide, and its entropy is 51.0 joules per Kelvin, minus the sum of our reactants. So then our reactants, I have 2 moles of aluminum, and its entropy is 28 joules per Kelvin, plus 3 moles of magnesium oxide, and its entropy is 27. All right, so then I am going to go ahead and simplify those and work them all out. So 3 times 33 plus 51. If you plug it into your reaction, I got 150 there. And then 2 times 28 plus 3 times 27, I got 137. there. So I have 150 minus 137. It gives me that my delta S of my reaction would be 13 joules per Kelvin, moles of our reaction, per mole of reaction. And that would be our delta S right there. So it's just products minus reactants. We see that this one is positive, so our entropy is increasing here. All right. I have a practice problem right here for you guys, so I want you to go ahead and pause the video and try this problem, see if you can do it, and then restart the video. All right, hopefully you paused it and worked it. Whenever I worked it out, I got negative 149 joules per Kelvin per mole of reaction. Okay, so that's our first part, is our entropy. So entropy is just, again, kind of a measure of disorder. And we've talked a little bit about how we can kind of predict the entropy of a reaction, and then as well actually solving for the change in entropy. So our next part of this is then free energy, or this is kind of the Gibbs part. So free energy is G. And we do have a nice equation. We kind of have two equations. Well, we have multiple equations we're going to learn with delta G, but two equations with solving delta G. So delta G is equal to delta H minus temperature times delta S. But basically, free energy change is a measure of the thermodynamic favorability or spontaneity of a reaction. It is the maximum work available from the system. All right. So a thermodynamically favored reaction carried out at a constant temperature and pressure has a negative delta G. Okay, so I'm just going to go ahead and say I really think the hardest part of what we are going to learn today is all of the different signs, because they can just get a little confusing with, okay, delta G has to be negative, but entropy has to be positive. So what does that mean? But yes, we will get through it together, guys. So I think the hardest part is the signs. So if I were you, I might make like a little cheat sheet for myself of the different signs. All right. Anyways, continuing on. So like I said, delta H is our enthalpy, delta S is our entropy that we just learned about, and then T is our temperature. Okay, so because delta G needs to be negative, and it's related by this equation that we've just talked about up here, that delta G is equal to delta H minus the temperature times our entropy, there are a few things we know are true. So if delta S is positive and delta H is negative, it will always be spontaneous at all temperatures. If S is positive and delta H is positive, it'll only be spontaneous at high temperatures. So if we have positive and positive, high temperatures. And then if delta S is negative and delta H is negative, it will only be spontaneous at low temps. And if S is negative and H is positive, it will be non-spontaneous at all temps. Okay, we will come back to that. We will definitely talk about that, but we are going to start by just talking about delta G, which is our standard free energy change. This is the change in energy that occur if the reactants in their standard states are converted to the products in their standard states. And once again, we have a very similar equation to the ones that we've learned. That is that the delta G is equal to the sum of the delta G of our products minus the sum of the delta G of our reactants at standard conditions. And then delta G of formation for a free element in its standard state is 0. So if I have like oxygen, just something that's an element by itself in its standard state, it will be 0. All right, so we are going to start with this first one, which says, given the equation N2O4 produces 2NO2 in the following data, calculate delta G. All right, so we are going to go ahead and do that. So delta G is equal to, and it gives us our delta G's down here, the sum of our delta G of our products, which would be 2 times the formation for NO2, which is 51.30, minus that of our reactants, which is going to be 97.82. All right, and we'll go ahead and solve that one. And when I do, I get that delta G is equal to 4.78 kilojoules per mole. So this one would be non-spontaneous because delta G is positive and delta G needs to be negative for a reaction to be thermodynamically favorable. All right, so now I want you guys to go ahead and solve this next one. So go ahead and pause the video and try to solve it. It's a little more complicated, but it's still not bad. Okay, so when I solved this one, I got that delta G would be negative 6 kilojoules per mole. We do have that negative delta G value, so this would be spontaneous under standard conditions. All right, sometimes you might be given the G's of formation or the Gibbs of formation, but most of the time we're probably going to be given delta H and delta S as well. All right, so this is the equation that we'll be using a lot, which is delta G is equal to our change in enthalpy minus our temperature times our change in entropy. Now, one really, really important thing to remember is that we have to change our S to kilojoules to kilojoules. So our S is in joules most of the time, so we have to just divide it by 1,000 in order to get it into kilojoules. All right, this is called the Gibbs-Helmholtz equation. All right, so this is again another way that we're able to remember and determine the thermodynamic favorability of a reaction. All right, so we're going to start with this first one, and it says for the given reaction and the following information, calculate the delta G at 25 degrees Celsius. And it gives us our reaction, then it gives us our delta H as a formation for our different products and reactants, as well as our delta S as well. All right, so in order to solve this one, we're going to use the Gibbs-Helmholtz equation. We are going to have to calculate the delta H of our reaction, as well as the delta S, and then plug that in to our delta G equation that we've been given. All right, now I know I didn't leave a whole bunch of space here, so I'm going to write as small as I possibly can over to the side, and you guys should do the same. All right, so let's go ahead and work this one. All right, so the first thing we need to do is solve for our delta H of our formation. So if you guys remember, there's a little reminder for us that delta H is equal to the sum of the heat of the delta H of our products minus the sum of the delta H of our reactants. So let's go ahead and solve for our delta H. So delta H is equal to 2 times negative 100 plus, and remember oxygen is going to be an element it's just an element, so its delta H will be 0 because it should not take any energy to form oxygen. So 2 times negative 100 plus 3 times 0 minus the sum of our reactants, which is going to be 2 times, because we have 2 lead oxides, times the heat of formation of lead oxide, which is negative 218, plus the sum of our the other reactant, which is SO2, so 2 times that, which would be negative 297. So go ahead, plug that into your calculator. And when you do, I got that delta H should be 830 kilojoules per mole. All right. And then we also need to solve for our delta S, and it gives us the values that we need. So our delta S is going to be equal to the sum of our entropies of our products, or sorry, of our reactants minus the sum of our entropies of our, wow, totally messed that up, guys. I'm so sorry. Sum of our entropies of our products minus the sum of the entropies of our reactants. So starting with my products, I have 2 times the entropy of my lead sulfide, which is going to be 91, plus the entropy of my oxygen. And entropies are not, like, even if it's an element by itself, they will have an entropy value. So they are not just 0. Minus the sum of my entropies of my reaction. It would be 2 times 70 plus 2 times 248. All right, so go ahead and plug that in to your calculator. And when I do, I got 161 joules per Kelvin mole of reaction. Now, remember, whenever we are solving in the Gibbs-Helmholtz equation, we do need to convert that from joules to kilojoules, so just divide by 1,000. And when you do that, I got 0.161 joules, kilojoules, not joules, kilojoules, because we've divided by 1,000, so we've converted into kilojoules. Goodness, I can't write this unit. Okay, now that we've solved for both of those, we can plug it into the Gibbs-Helmholtz equation. All right, one thing to note is that our temperature does need to be in Kelvin. So remember, nice and easy conversion into Kelvin is just to add 273. So 25 plus 273 gives me 298 Kelvin. So plugging it into my calculator, I have delta G is equal to my delta H, which in this case is 830 kilojoules per mole, minus my temperature, 298, times my delta S. And when I solve that, I get, plug it into your calculator, I get that delta G is 782 kilojoules per mole. All right. So we have 2 more delta G problems, one of them also involving solving, and then one of them is a little bit more of a conceptual problem. So I want you guys to go ahead and take a minute and solve both of these problems. All right, so go ahead, solve both of them, pause the video, and then come back to go over them. All right, guys, so for this first one, we had to calculate delta H, delta S, and then use those 2 values to calculate delta G. So again, for my delta H, I got negative 200 kilojoules per mole. For my delta S, I got negative 187 joules per Kelvin times moles. But don't forget, we do have to convert that to kilojoules to be able to use it in the Gibbs-Helmholtz equation. And so when I do that, and I plug it all in, I got that my delta G would be negative 144 kilojoules per mole. All right, and then for my last one, it was a little bit more conceptual, but it did involve some math. And it wants to know when will it change from spontaneous to non-spontaneous. So you guys, we can remember that a reaction proceeds spontaneously when our delta G is negative, right? So when our delta G is negative, so it would switch whenever our delta G is 0. So I put in 0 and I got that the temperature it would switch at would be 467 Kelvin. Right, I just plugged it in and did some simple algebra there. All right, let's talk about our last thing, and that is coupled reactions. And coupled reactions is going to be very similar to something we've talked about in the past. So we can add equations similarly to Hess's law method of determining our enthalpy. So remember that when delta G is positive, the reaction is thermodynamically unfavorable. However, we can take an unfavorable reaction and couple it or partner it with a favorable reaction to make the overall process favorable. However, they must have a common intermediate for this to occur. So remember, an intermediate is something that is produced in one step of a reaction and then used up in a subsequent step. So we have to have something produced in one reaction and used in the next reaction. All right, so let's work a problem. Again, very similar to Hess's law. So let's start with this one. So if we're given this equation, these two equations, we want to calculate delta G for this reaction. All right, so let's go back to our Hess's law brains and think about Hess's law. So we can see that we have Fe2O3, we have Fe2O3 in this one. All right, we have 3CO. We have CO in this one, but it's just one, so we're going to need to multiply this entire reaction by 3 and also multiply our delta G times 3. So I can rewrite that as 3CO plus 3 halves O2 yields 3CO2. And then my delta G would also be multiplied by 3. So my delta G would be equal to, let me see. I plug it into my equation, I got 850.5 kilojoules. All right, so I don't need this one anymore. All right, 3 halves O2 is produced in this reaction and then consumed in this reaction. So that's our intermediate. We have 2 iron and 3 CO2. So everything adds up, and this gives us our overall equation that we're looking for. So then all we do is add our delta G's together. So we have 742.2 plus negative 850.5. So I'll add those two together. So 742.2 plus negative 850.5. Add them together and I get negative 108.3 as my delta G value. That is negative. So this reaction would happen because, again, we coupled that non-favorable reaction with a favorable reaction. And it's very similar to Hess's law. All right, so you guys go ahead and work this next one. So pause the video and work this problem. All right, when I solved that one, I got that my delta, I didn't have to manipulate anything up here. S is my intermediate that is produced in one reaction and then used in the next. And I got that my delta G would be negative 101.8 kilojoules. Okay, guys, well, this is the first part of our Unit 9. Hope it made sense. Feel free to email me if you have any questions. All right, have a great day.